Okay, this is Math 105, Section 1.2, Part B. Okay, now we're talking about radicals. Some of this notation is a little off, so let's kind of start here. This radical symbol means square root. When we don't have a number here next to the radical symbol, it means square root. Sometimes we'll put a 2 there, but you don't have to. So square root of a equals b means b squared equals a. So let me rewrite that. So we can say square root of 9 equals 3 is the same thing as saying 3 squared equals 9. Okay, so let's focus on that instead. We'll look at that as an example. Okay, so what we're doing is we're taking a exponent backwards. In other words, when we say square root of 9, we're saying what number squared gives you 9? And that would be 3. So we're saying 3 squared gives you 9. So what we're doing is we're kind of doing an exponent backwards. Okay. Now we can only do this when this number is greater or equal to 0. Okay. And the reason for that is because you can't square a number and get a negative, right? So you can't have a negative inside a square root. Okay. So when we say square root of a equals b, that means b squared equals a. That should be b squared there. And we can say b has to be, this should be greater or equal to 0. Okay, so let me rewrite that here. Okay, so this says b squared equals a, okay, and b has to be positive or 0. Okay, so let me scratch that. Okay. Now we can extend that to higher roots. Okay, so if you see a number here in that little crutch of the radical, that means your nth root. In other words, we're looking for a number that we can multiply n times to get a. So when we get our answer, we're going to take b to the n to get a. Okay, and we call that the nth root. Okay, if that root is even, then we have to have a be positive or 0. In other words, we can't take an even root of a negative number. Okay, and our answer will always be positive or 0 as well. So, for example, let's just go back to our square root example. Okay, if we're taking the square root of 4, okay, that would be 2 because 2 squared equals 4, right? Okay. Notice that this is positive and this is positive. Okay, they could be 0 as well, but they can't be negative because you can't multiply a negative. You can't multiply something twice and get a negative, right? And when we're talking about even roots, we're always talking about the principal root. So we're always going to use our positive answer. Okay. Same thing. Let's do like the fourth root of 16. Okay. Now that would be what number to the fourth power gives us 16, and that would be 2. So 2 to the fourth equals 16, right? Okay. That's another way to look at that. So the fourth root of 16 is equal to 2. Okay. So notice we have to have a positive here. We're not going to say negative 2. Even though negative 2 to the fourth is 16, we're going to use positive 2 as our answer. We call that the principal root, and that's for even roots. Okay, we use what's called the principal root, which is the positive. Okay, in both of these cases. Okay. So here's some properties of roots, and we're talking about nth roots in general. So it could be square root, could be cube root, could be fourth root. If we're taking roots of a times b, we can break those out. So the nth root of a times b is nth root of a times nth root of b. Okay. In this case, we're looking at minus 8 times 27 for cube root, which means we can break those out. Now we can take odd roots of negative numbers because if we multiply something 3 times and it's a negative, we're going to get a negative answer. So minus 2 cubed gives us minus 8. So this actually we can do for odd roots. We can have negatives for odd roots. The cube root of 27 is 3. 3 times 3 times 3 is 27. So this would be minus 6 as our answer. Same with dividing. If you're taking the nth root of a divided by b, you can break those out separately as separate roots. Nth root of a divided by nth root of b. So in this case, 16 over 81, we can take the fourth root of 16 over the fourth root of 81, which is 2 over 3. This one's a little bit different, but if we're taking an nth root and then taking another root of that, we can combine those as a single root multiplying. Okay, and I'll write a little aside here. We can write it like this. The nth root of a is the same thing as writing it where we take the nth root first, okay, and then take the nth root. Okay, so we'll look at that again in another slide, but basically it doesn't matter which root you take first. Okay. So what we're doing is multiplying those, right? Okay, so the square root of the cube root of 729 is the same root as the sixth root of 729, which is 3. Okay. If we take the nth root of a to the n, now this is undoing that exponent. So that's true if n is odd. Okay. So in other words, like the cube root of 2 cubed is 2. Okay. Or the cube root of minus 5 cubed is minus 5. Okay. It undoes that exponent. 5, if n is even, if you're talking about an even root, then you have to take the absolute value of a, because we could take, we could say like minus 3 to the fourth, right? Which is 81, right? We take the fourth root of that, we get 81, but that's not minus 3, that's going to be 3, right? So we have to take the absolute value. So you can take minus 3 inside your radical if you take it to an even power, but realize that your answer will not be minus 3, it will be plus 3, okay? So this undoes it, but we have to say absolute value of a, because we could have a be negative in this case. Okay, this is when n is even, and we're taking an nth root. So let's look at a couple examples here, and we'll look at more in class, but here we're taking the cube root of x to the fourth. Now what we're going to do is break out x to the fourth so we have a perfect cube there, and then we're going to use our properties to break these out. So the cube root of x cubed is just x, okay, and that's using property 4. And then this cube root of x is just cube root of x, so we kind of stuck with that. So we can take an x out, okay. And then here we're going to do these all separately. So the fourth root of 81 times the fourth root of x to the 8th times the fourth root of y to the 4th. And here, because that's even, our answer for y is going to be, fourth root of y to the 4th is going to be absolute value of y. Okay, we're not going to get too picky about that as we do these problems, but just kind of initially we'll do that. Okay, let's look at the x to the 8th. So that's x squared to the 4th is x to the 8th, right? And if we take the fourth root of that, we get x squared. Okay, and then the fourth root of 81 is 3. So we have 3x squared times the absolute value of y, or we can just say 3x squared to y in general. Okay, when we're combining radicals, we're going to try and simplify them. So here we're looking at square roots. We're going to look for perfect squares that factor out of these numbers, the highest perfect squares. Okay, so 32 is 16 times 2. 16 is a perfect square. And we're going to factor that out because we can take the square root of that and get 4. Okay, and for 200 we can factor out the highest perfect square is 100. That factors out, and so we can break those out and take the square root of 100, which is 10. Now we call these things like radicals. What this 4 is multiplying times square root of 2, and we're multiplying 10 times the square root of 2. So we can say, the square root of 2, it's an irrational number, right? We have 4 of these plus 10 of these. Both of these, right? So we add those together, we get 14 of those. Okay, so we say 14 times the square root of 2. So that's how we would simplify that. We want to take all the perfect squares out of 32 and 200. Okay. Here we're doing something we're subtracting, right? So here we can take the 25 out because that's a perfect square, right? And we can take the b squared out of the b cubed because that's a perfect square. So that gives us 5, square root of 25, times the square root of b, minus b, which is the square root of b squared, times the square root of b. And then that would be, here we have 5 of these minus b of these. So 5 minus b of those, of the square root of b's. Okay, so we're combining these as like radicals. Okay, so what we can do with these radicals, we can turn them into what we call rational ratios, exponents. So the nth root of a is a to the 1 over n. We don't have to write it with a radical sign. We can write it as a to the 1 over n. So for example, the square root of x would be x to the 1/2. Okay. The cube root of y would be y to the 1/3. Okay. And we can do this with numbers as well. So we could say like the fourth root of 5 is 5 to the 1/4. Okay. So we can treat these as exponents because they are exponents. They are fractional exponents. We say rational, meaning fractional. Okay. So now when we have a fractional exponent with an m on the top and an n on the bottom, we can do two things. Now that numerator is the regular exponent, that denominator is a radical or a root, okay? So what we can do is say this, okay, well, a to the m over n is equal to, here we're going to do the root first, a to the 1 over n times m, okay? Now, what I did was I broke out that fraction, so it's in two parts, okay? And that's equal to a to the 1 over n in parentheses to the mth power. And I'm just using my powers of exponents, my rules of exponents there. And then we can write that as a radical, writing it like this. The nth root of a, which is a to the 1 over n, to the mth power, okay? So that's how we get that first thing there, okay? The second one, we're just doing the opposite. We're going to do the exponent first and then the root. Okay, so whenever you see these fractional exponents, there's two parts to it. The top part is a regular exponent and the bottom part is a root. Okay, so we're doing, and it doesn't matter which order you do them in first. Okay, either order is fine. Okay, but keep in mind that if n is even, then we require that whatever's, a has to be greater than or equal to 0 because we're taking an even root because that n is a root. Okay. Here's an example with rational exponents. Now what I like to do is just deal with the negative exponents at the end, so don't worry about moving things around yet. But we're going to use our powers of exponents here, so properties. So I have 2x to the 3/4 y to the 1/3 to the third power, so that's going to means I'm going to take 2 to the third power times x to the 3/4 to the third power divided by y to the 1/3 to the 3 power. So every part of this gets that third power. Okay, and then here we just have y to the 4th over x to the minus 1/2. Again, you can move this if you want, but I tend to take care of the negative exponents as my last step. Okay, so 2 cubed is 8. X to the 3/4 cubed, I multiply to get x to the 9/4. Y to the 1/3 cubed, okay, is just y to the 1. 1/3 times 3 is 1. And then I have y to the 4th, and we actually moved the x to the minus 1/2 up to the top. Here is x to the plus 1/2. That's fine. Okay. Now we're going to group the x's together. Now we can skip the step, and we did here, but we're just going to add these exponents. So 9/4 plus 1/2, which is 2/4, is 11/4. So there's x to the 11/4. And then here we're dividing. So we're taking y to the 4th divided by y to the 1, which gives us y to the 4 minus 1, which is y cubed. So there's our final answer. And we can leave this in exponential form, in rational exponential form. We don't have to put it as a radical, okay? So yes, this would be a 4th root of x to the 11th, but we don't need to write it that way. Okay, one thing we want to do when we have a denominator with a square root or any kind of root in it is we want to get rid of it. Okay, we don't want it in the denominator. We call that rationalizing the denominator. So we eliminate a radical or a root in the denominator. Okay, if you just have like a square root in the denominator, okay, we can multiply it times that square root on the top and the bottom, and what that does is it gets rid of the square root on the bottom. So now square root of a times square root of a is just as a, right? So but make sure you multiply the top and the bottom times the same thing, but we get square root of a over a as our answer there. Okay, the first one, a here, we have 2 over square root of 3. Okay, so we want to get rid of that square root of 3 in the denominator. So if we multiply times the square root of 3 over square root of 3, this becomes 3 on the denominator. So what we end up with is 2 times the square root of 3 over 3. So that eliminates the square root in the denominator here. When you have a higher root, like a cube root, or in this case a 7th root, okay, it's a little bit different. Okay, we don't want a perfect square. We want a perfect cube, right? So in order to get a perfect cube, we're not going to multiply times the cube root of x squared, because that will give us x to the cube root of x to the 4th, but we just multiply times the cube root of x. Okay, and when we do that, we get cube root of x cubed, and see that will eliminate, that becomes x, right? So we're going to multiply times the cube root of x over cube root of x here, okay? Because we want to get a perfect cube, not a perfect square. Okay, in fact, we already have a perfect square, right? But we're taking a cube root, right? Okay, so that will, when we multiply cube root of x over cube root of x times this, we get cube root of x over cube root of x cubed, which is just x. See, we get rid of that root in the denominator. Okay. This one, c, now we have, now we're taking, what we're doing is we're taking the 7th root of 1 in the numerator, which is just 1, so that's why that becomes a 1 there. And then in the denominator, we're taking the 7th root of a squared. Okay. Now, we don't want a perfect square, we don't want a perfect cube, we want a perfect 7th power, because we're taking a 7th root, right? So we're going to have to multiply this times the 7th root of a to the 5th, so we get that 7th root of a to the 7th. So here we have to multiply times 7th root of a to the 5th over 7th root of a to the 5th, okay, to get that, right? Because this cancels, 7th root of a to the 7th. Okay, so that gives us 7th root of a to the 5th over a, because the 7th root of a to the 7th is a. Okay, that's the end of section 1-2 as far as we'll cover in this little presentation, and we will go over examples in class in a little more detail.